Hello, my name is Aidan Prouty. I am an aeronautical engineering student at Embry-Riddle Aeronautical University. Um, I am really excited to teach math. I feel like I've learned a lot about math in college, pursuing my degree, and I'd like to help kids understand it better because I know that I was very scared of math, especially in high school. Um, to the point where it almost turned me off of going into engineering and pursuing a STEM degree. Um, I think that getting the core concepts of math down early and building those initial assumptions is very important. So I would like to just explain things in a nice, simple way, in an empathetic way as well, and just help kids build a solid base so they can learn more math and realize how cool it is. So specifically, the class that I would love to teach is calculus. I think calculus is really really cool. I've been through calculus 1 through 3. Um, I did pretty well in all of them. And now I'm in differential equations, applying all the concepts of calculus to the real world. And so today, I thought that I would just explain three simple concepts from calculus, and explain how they're going to be used, the notations, and explain what they look like graphically. So I want to start out first with limits. I hope you can see that. It's reversed for me. So I'll take a function, f of x equals x minus 1 over x minus 1. And that just looks like this, a straight line. Except when you plug in 1, it ends up being 0 over 0. Now, anything divided by 0 is undefined. There's nothing there. So you represent that on the graph. I represented it by just drawing a little red circle here because there's no line there. It's undefined. Now, there is a way that you can find the value as the function approaches 1. And that's what you say. You say it approaches it. It's not when it's at 1 because the line never quite reaches 1. It's undefined there. So that concept is called a limit. And when I say approaches, this is what I mean. That's why I wrote the two little red arrows here. It's as the line gets closer and closer and closer to 1. You can zoom in insanely far, and you'll see the line. It keeps getting closer. It gets closer forever, but it never quite reaches 1. And so you write it like this. This is a notation. You write lim or limit as x approaches 1 of your function. Now, when you want to compute a limit or get a value out of it, get something useful out of it, all you do is you take the number here that it's approaching and you just plug it into your function and you get an answer. And we can say that because, again, as I was saying earlier, when you zoom into the function, it gets super, super close, but it never quite gets there. It gets so close that it's okay to just approximate it at that value. So that's why you can just plug in 1 in this case. Now, a cool thing you can actually do, at least I think it's cool, it kind of blew my mind initially when I first learned about it. Cool thing you can do with limits is you can actually plug in infinity, and you can find what functions do all the way up to infinity and down to negative infinity. Now, usually in your math classes, or you're told by your math teachers that infinity isn't a number. You can't really do anything with it. It's just kind of there as like a representation of a huge number. Well, you actually can do stuff with it. So let's take this function here, 1 over x. Looks like this. Now these lines never actually quite reach the y-axis. So what you say is the limit of this function as it approaches infinity, that's what you say, the limit of the function as it approaches infinity. And if you wanted to find what that value is, all you do is plug in infinity into this fraction here, or into x. And now something divided by infinity, you can't put that in a calculator, but you can think of it like instead of plugging in infinity, think of it like plugging in like a trillion, like 1 over a trillion. That's a really, really, really small number, right? So you can just say it's 0. That's all infinity is. It's just a ridiculously, unimaginably large number. So it makes sense that this is just 0, right? Okay, so that's limits. I'll move on to next, derivatives. So normally, when you want to find the slope, like the rate of change of a line, say y equals x here, just a nice straight line, all you do is you take the rise, this little red line here, I represent it up here, and over the run of the line down here, and you divide the two. So rise divided by run, that gives you the slope. In this case, it would be the rise is 1, the run is 1, 1 divided by 1, the slope is 1. Well, that's with straight lines. Say we have a function like f of x equals x squared. This is a parabola. It's a curvy line. It's constantly changing its slope. You can't just say, oh, well, the rise here is 1 and the run here is 1, because it's different here and it's different here and it's different here and it's different way up here. So you need something called a derivative and something called the instantaneous rate of change. You use derivatives to find the instantaneous rate of change, I mean. And you can kind of think of that like a video of a runner, I guess, or like a video of a race car that's constantly accelerating. You can't just say it's going 50 miles an hour because it's accelerating. It's constantly gaining speed. So what you do is you just pause the video and you look at your accelerometer and you just look at the speed because it's paused. That's kind of what a derivative does. It pauses the function at a moment. And that's what I represented here with this red line. That's the slope at this specific point. Now, the way you find a derivative, or I guess I'll start, the way you write a derivative, there are two ways to write it, actually. You can say d over dx of your function, in this case, x squared. The answer to that would be 2x. I'll get into finding the answer later. You can also write it like this in prime notation. This is also called Lagrange notation. And you just write a little apostrophe there. That's called a prime. And again, the answer is 2x. Personally, I like Leibniz notation because it's more clear. It more clearly lays out like what variables you're taking the derivatives of. As you get into higher level math classes, you have to take the derivatives of functions that have more than one variable in them. So it's useful to write that all out. But whatever works for you for now is the best, obviously. So in general, the way to find the answer to a derivative is you take the derivative d dx of x to the n, and can be any number, equals n times x minus 1. So all you do is you take the power, you move it to the front, and then you subtract 1 from the power. Really easy, right? Nice and easy. Derivatives were my favorite because they were so easy. I thought calculus would be scary, but it's literally that easy. So I have some examples here. I wrote them in different notations just so you get comfortable with them. So the derivative of x cubed, x to the third, is you take the power, move it to the front, so it's 3 times x, subtract 1 from the power, 3 minus 1 is 2, so the answer is 3x squared. Now you have d dx, the derivative of x to the negative 2. Now don't be scared of the negative. Just follow the rules. Move the negative 2 to the front and subtract 1. Negative 2 minus 1 is negative 3. So the answer is negative 2x to the negative 3. Now you can also, sometimes you need to take more than one derivative. Sorry, that's my roommate coughing. You need to take more than two derivatives. So you'd write it like this, with 2 primes. In Leibniz notation, you write it d squared over dx squared to denote how many times you're taking the derivative. Now, I like to do it one step at a time because when I do it in my head, I usually screw something up. So I take it nice and slow. So you take the first derivative, it's 4x to the third. Take the second derivative, you move 3 down to the front. 3 times 4 is 12, and you subtract 1 again, and so you get 12x squared. Next, I have the derivative of x, just x. So you take the 1, because technically it is to the power of 1. So you take the 1, move to the front, subtract 1. 1 minus 1 is 0. And any number to the 0 is just 1. So the answer to this is 1. Now, the next one I have is the derivative of 4,452,020. That's just 0 because there's no x in it. And uh, any number without an x in it is just a straight line on the graph. It doesn't have a slope. The slope is 0. So it would make sense that the derivative is also 0. And that goes for any constant. Now, the last thing I'd like to explain, I know I'm a little over time here, is integrals. Now, integrals are something for like higher level calculus, or not higher level, but like Calc 2 and stuff, into Calc 3. You'll learn more about it like as you get further up into Calc, but I just want to start by explaining them because they're very, very important. So I'll just jump straight into it. An integral is the sum under a curve. I have written down here f of x equals ln of x, this nice curvy line here. And I have these bounds 2 and 3. And when you take the integral of it, you find this area in here. I have these boxes drawn in here because I'll explain that later. But it's basically a simple visual way to explain like what exactly we're doing when we're finding that sum. In a way, not in a way, integrals are an infinite sum. You're summing something infinitely many times. This is denoted, this is a little confusing, but this is the formal definition of it. I'll try to explain it simply. So the definition of it is, remember your limits. So the limit as n approaches infinity of the sum, that's what this weird like e thing is. It's the Greek letter sigma. Limit as n approaches infinity of I equals 1. I is like the initial, the starting point where you're counting. So you start at 1. If I was 0, you'd start counting at 0. If I was 50,000, you'd start counting at 50,000. But here we're starting counting at 1. So I equals 1 to the n. Remember, you just plug in infinity. So 1 to infinity. This is summing something from 1 all the way up to infinity. That's a crazy amount of numbers. Again, an infinite sum. Of f of x I delta x. Now, that equals this. This is how you write an integral. It's this funny looking S thing with your bounds top and bottom. So like if, say here, my bounds would be 2 and 3. So I would say here, A equals 2 and B equals 3. Those are my bounds. I'll end up plugging those in later after I take the integral to actually get a constant value out of this. But you don't always have to have bounds. I'll get into that in a bit. Of your function f of x, dx. Make sure to include dx. Dx is like the way of clarifying what variable you're trying to take the integral of. If I had a function that had x and y in it, and I only wanted to take the derivative, the integral of the y variables, I would say dy instead of dx. So this is important that you include that. You can't leave that out. So in general, the way to solve an integral, so we have the integral from a to b of x to the n dx. Basically, you pull the power down to the denominator. You'll end up with a fraction as an answer. Pull the power down to the denominator, add 1, and then also add 1 to the power. Now, if you're astute, you may have noticed that this is literally the exact opposite of a derivative. It's called an antiderivative. Or an integral. Literally, the exact opposite. Integrals and derivatives are very, very closely related, which is a little hard to show graphically, so I'll just tell you that straight away. It kind of makes it like less scary, all of it, just to know it's all interconnected. You also don't forget your bounds. You include your bounds in your answer by drawing this little bar and including your bounds A and B. And then to get a number out of this, you just plug in your bounds. You start with B, and then you subtract A, plugged in the same function. So I have some examples here. The integral of 1 to 2 of x squared dx. So you pull the power down and add 1. So x over 3, and add 1 to the power. So x cubed over 3 is your answer. Is your integrated function. That's what it's called. It's called an integrated function from 1 to 2. And then you plug in 2. So it's 2 cubed over 3 minus 1 cubed over 3, which is 8 over 3 minus 1 over 3, which is just 7 over 3. Now, another thing I have that this is more just like a concept I want to show you. So this is the integral from 0 to 1 of x to the fourth plus 2x dx. Now, that may look a little scary, like oh, what do you do? There's kind of a wrench in my plans there. How do I do that? There's a plus in there. Well, integrals are nice to us, and you can actually split that up into two integrals. So you have the integral from 0 to 1 of x to the fourth, plus, you still have to include your plus, that doesn't go away, the integral from 0 to 1 of 2x dx. So you end up just doing two integrals, and then you just do them like normal, and then you add them once you're done. And that's your answer. I didn't get an answer because I ran out of space there, but you get the concept, hopefully. I really just wanted to show how you can do that. And finally, we have the integral of 1 over x dx. The answer to that is ln, absolute value of x. If you're not familiar with absolute value, it's basically just saying drop the negative. So like the absolute value of negative 4 is 4, and the absolute value of 4 is 4. Now, you might notice that I didn't include bounds on this one. That's not a mistake. This is called an indefinite integral. These are called definite integrals because the bounds are defined. The bounds are not defined here, so it's an indefinite integral. So that means you're literally finding the area under the entire curve, which is infinity, but you want an answer out of this. So you represent the rest of that area with this, c, or a constant. And when you're taking in-depth, you'll usually start, when you learn about integrals, you'll start with indefinite integrals. So make sure you always include c. Your professors or teachers will hammer that into you. You have to include c. It is important. It gets more important in Calc 3 and DiffEq, but just for now, just make sure to include it. So that's all I have. Sorry, I went pretty over time. But yeah, just wanted to explain some simple concepts and show you, I guess, my teaching style. Have a good day.